So hello everybody to our Gamma seminar. Today we have a special session because it's for students who are going to present their works soon. So we have two talks, one by Daniel Spisak about the Energy-Casimir method and another one by Alvin Surya, who is going to talk about geometric quantization. So yes, as usual, please make questions, comments as normally. That's everything we have to do. Yes, remember that these are students and they are very young. Yeah, they are both. Well, Daniel is in his third year and Avin is in his fourth, preparing for his fifth. So it's preparing his master thesis very soon. So take it easy. Okay, and after that, let's go. So, Daniel, are you ready?
Yes.
So
Hi.
please go ahead.
Yes. Good morning. I would like to introduce to you the Energy-Casimir method. First, I will start by motivating it and selling you the idea how it came to be and the problems that we had before the method was discovered. Then I will introduce the basics of Poisson geometry. Then I will go on to the basics of Lyapunov stability theory. And finally, I will formulate the Casimir energy method and apply it to a free rigid body in a specific case, easy to calculate. So yes, so what is Energy-Casimir method and how it came to be? So the fundamental problem we are going to discuss today is the stability of the Hamiltonian systems. And Hamiltonian consider a Hamiltonian systems with an equilibrium. Hamiltonian system is given by this expression, and what we had before the Energy-Casimir method, we usually use the classical Lagrange-Dirichlet criterion, which determine the stability of the equilibrium. And if the first variation of the Hamiltonian at this equilibrium is vanishes and the second variation is definite, then we call this equilibrium stable formally. And the problems arise when in many physical systems and we are not able to, this criterion does not yield anything we can use. So for instance, it fails in often in reduced Hamiltonian systems, usually sometimes after Poisson reduction, the Hamiltonian is constant on coadjoint orbits. And so the equilibria are not isolated extremely of H. So we cannot, this criterion doesn't give us anything. And for instance, consider a free rigid body. And in after Poisson reduction, the Hamiltonian is given in this form, where the large P is the angular momentum and the I in the between is the inertia tensor. And it is constant on the entire sphere. And when we go back on the unreduced space, the first variation at the equilibrium is not zero. It is normal to the sphere, meaning that this equilibrium is not a standard critical point, and the classical criterion fails. And
Daniel,
this talk, I will.
Yeah, yes, a comment. Normally, this happens with systems that they have symmetries, because due to the symmetry, the critical point is not isolated. Yeah, it's a 1/13.8 move. So that's why symmetries are important. This method is something important. Thank you.
I will also thank you. I will also discuss the stability modulo in systems with symmetry and why the Energy-Casimir is very good at it. Okay, so the solution is to, okay, so we want to add something, modify the Hamiltonian so that the critical and equilibria points align. And we want to add something that does not change the dynamics of the system. And we will be using the Poisson geometrical structure. Explicitly, we'll use Casimirs. So now I will introduce some basics of Poisson geometry, and we begin by definition of a Poisson manifold. It is a pair M manifold and a bracket over smooth functions that is bilinear, anti-symmetric, and satisfies Jacobi identity and Leibniz rule. Equivalently, there is an equivalent definition that arises from the Leibniz rule, and the Leibniz rule implies the existence of a unique vector field such that this vector with contracted with the differentials is exactly the bracket of those smooth functions. Then the Jacobi identity is equivalent to Schouten-Naenhuis self-bracket condition, that is, taking the b vector with itself in the Schouten-Naenhuis bracket, we get 0. And yeah, the Schouten-Naenhuis bracket is the generalization of the standard Lie bracket to Pauli vector fields. Now, the basic example of a Poisson manifold is, I think the most simple one is Poisson. And we do this by defining the Poisson structure by taking the inverse of the symplectic structure. So this is the Poisson tensor, when we define it as the inverse of the musical isomorphism that is induced by the symplectic tooth. And this is
Daniel, sorry,
yes.
just one remark. This is the one of the most natural, but it's not the simplest. I mean, if you have a vector that's equal to 0, it will be Poisson. Yeah.
Okay. Yes.
This is the most. This is just 0. So every pair of effects is maybe to 0, and there's 0. Okay. This is the one of the most natural, and then what they come from.
Yes.
Thank you.
Okay. Thank you for the intuition behind it. This is the dual on the Poisson structure on a dual to the Lie algebra is very important example, and we'll be using it. So consider a finite dimensional Lie algebra. Dual to it carries the Lie Poisson bracket defined in this way, and it is very straightforward to show that indeed it is a Poisson bracket. And when we use those two identities, the isomorphism, and we can easily show that it is truly Poisson bracket. So a few things that now I will go on a few things that also happen in Poisson manifolds. So yes, the Poisson B vector induces a bundle map. This is the Poisson tensor. It is defined by this expression. Then the Hamiltonian fields of some smooth functions are defined in this way. And we know that the Lie derivative and direction of a field over some smooth function, just this field taking the function. And this is by definition just the Poisson bracket of those two functions.
Sorry, Daniel, do you know any other convention for that? For defining the Hamiltonian vector field and the Poisson bracket?
Sorry?
Do you know any other convention to define the Hamiltonian vector field of a function in Poisson manifold?
Yes, we could use the derivative of the from the Poisson cohomology, I think. Yeah.
I mean, the answer is the pi. The definition of the Hamiltonian vector field you use is the mathematical one. If you define like here, but with a minus, is the definition that is used normally in physics. Okay. And the Poisson, this first is with a minus in geometric mechanics normally. Yeah, physicists they use. The one you use is with for physics, for mathematicians rather. And with this second convention, okay, the Poisson bracket of function fg is the other way around. Is indeed minus the Hamiltonian vector field of f acting on g. And it's practical to know both conventions, because depending on the work you read, it's in one manner or the other. Okay, thank you.
Yes, thank you. Yeah, so indeed there is two sign conventions. The classical way for physicists use minus because it's a tradition, and mathematicians use plus because it's easier than to do using with morphism, having fun with morphisms, and it's easier. And also we define the characteristic distribution at some point as the image of the Poisson tensor at some point. And indeed, one can show that it is involutive. So by Frobenius' theorem, it can be generalized by using also Sussman generalization. It integrates the possibly singular foliation. And putting this together into the theorem, very clear of Constance Surya, then the integral manifolds of the characteristic distributions called this partition M in this manner, where S are symplectic leaves, S alpha. So every Poisson manifold is a disjoint union of symplectic leaves. And each leaf carries a natural symplectic form, and it is determined by this expression. And in consequence, the leaf dimensions are even because it is because they are symplectic manifolds, and they may vary across M. It is important to know that they may vary across the whole manifold. And points where the Poisson tensor vanishes are zero-dimensional leaves. That is the fixed points of every Hamiltonian flow. I want to look locally the Poisson B vector. How does it look like in coordinate? And Weinstein proved this theorem in 1983. So let's consider a Poisson manifold at any point with the constant rank, even rank of the Poisson B vector. There exists local coordinates such that the Poisson B vector is given in this form. And where the phi, alpha, beta are smooth functions that vanish at zero. And you can see that, okay, this looks like a symplectic part, and this is like something new. This is the stricter Poisson part. And the interpretation is that near every point, the Poisson manifold factors locally as the symplectic part, and the Travers stricter Poisson part. Yep. Now we define Casimirs. They have very important properties, and they appear also in Dirac geometry, and their geometrical meaning is not so trivial as one might think by just this definition. However, for this method, it is sufficient to just use this definition. So a Casimir is a smooth function such that for every other smooth function on this manifold, the Poisson bracket vanishes. Equivalently, the derivative at some point is in the kernel of the Poisson tensor at this point. And this happens for every point in the manifold. So it is from this manifold definition, what we get immediately that any Casimir is a first integral of every Hamiltonian flow. That is, okay, we take derivative, lead derivative of this Casimir, and indeed, as we showed earlier, it is just it is zero. And if the foliation, this is not strictly necessary, but it is nice to know that if the foliation is regular of codimension M, there are locally exactly M independent Casimirs. And by independent, I mean when we wedge over all of them, we get it is non-zero. So how to imagine a Poisson manifold? So this is a proposition. Okay, so we have a Poisson manifold, and S are symplectic leaves. And those symplectic leaves, there are Casimirs that are constant, and those for instance, if we have some Hamiltonian dynamics, the Hamiltonian dynamics does not leave the leaf because it is constrained by Casimirs. So, yep. For instance, a Casimir consider Poisson manifold is that is the dual to the Lie algebra SO3. It has symplectic leaf equal to the concentric spheres of the radius of the large P. It is in physical interpretation. This is a angular momentum at the origin, and the Casimir is just this radius square. So now we move on to the basics of Lyapunov stability theory. So consider an autonomous Hamiltonian system with on a smooth manifold. It doesn't need to be Poisson, and with an equilibrium. We say that equilibrium is Lyapunov stable if for every epsilon greater than 0 there exists delta greater than 0, such that the distance of at 0 of this solution from the equilibrium is less than delta implies that for all t the distance is also. So basically this definition says, okay, if we have a point near the equilibrium, it will stay in the close neighborhood of the equilibrium. Now we present a theorem by Lyapunov, and this is a theorem that we'll be using, and the classical Lagrange using. And consider a C1 function on open neighborhood of the equilibrium point, and if it satisfies those two things, we say that it is a Lyapunov function, and we can say that this equilibrium is Lyapunov stable. That is, it vanishes at this equilibrium, is greater from in the neighborhood of the equilibrium, and the first derivative given by this is a contraction. It is you can write this as a contraction, or this is written as a dual pairing. It's less than 0 on the neighborhood, and this is in. There is one definition. So in systems, when we have group symmetry, the correct notion of stability is given by stability modulo G. There's the modulo of the group, and I will let's just define, and I will explain a little bit more what's going on. So we say that this equilibrium is a Lyapunov stable modulo G if for every G invariant neighborhood of U, the orbit there exists a G invariant neighborhood V that is in U of this orbit such that the trajectory starting in V remain in U for all T. Okay, and what is this stability modulo G and why we need it? So if a system has a symmetry group G, the equilibria are not isolated points, but rather they are orbits, the whole orbits, and this mole perturbation shifts the system around the orbit, causing the standard Lyapunov stability to fail. And we usually fix this by projecting to the system with an explicit quotient space to collapse the orbits into isolated points. So, okay, I hope it won't jump too much. Okay. So here we have this is an orbit, and consider an equilibrium. Okay, we have an equilibrium, and we can move using the group action. Okay, but when we move from this point to this point, the Lyapunov stability classical part says, okay, we left the neighborhood of this equilibrium, and it is no longer Lyapunov stable, which is not actually the case, because even though the group action doesn't change the equilibrium status. So to fix this, we define stability modulo a group. So, okay, if we have an orbit, okay, we start here, and we want this trajectory to just stay in this neighborhood. And usually we would, usually what we would do is to Poisson out this group. So this whole orbit would be just an equilibrium point, and we would get this this classical formation of Lyapunov stability will work out. And with the Energy-Casimir method, instead of performing the explicit geometric reduction, we'll use the Casimir functions to achieve this quotient implicitly. And yes, so now we'll formulate the Energy-Casimir method. So let's just do a setup and review our strategy. So consider a Poisson manifold with a Hamiltonian and equilibrium, and C and K independent Casimirs. Independent is that we take wedge over those Casimirs and it is non-zero. Okay, we define a function C that is a tuple of all of those Casimirs. Now we choose a smooth function over then an open subset of Rk such that the image of this function C stays in U. And now we construct we modify the Hamiltonian by adding a composition of phi and C. The goal is to choose phi such that the first variation is evaluated at the equilibrium point is 0, and the second variation is definite on the tangent space to the symplectic leaf. And okay, if you probably heard about Casimir energy method, you probably heard about this formulation. Okay, we have Hamiltonian, we just add a Casimir, it is okay. However, for me, this formulation lacks the intuition how to apply it. Because, for instance, so this is equivalent formulation of the method. However, here we actually have look at what's under the mask, and it is, at least for me, easier to apply it and build an intuition what is actually happening during the application. And here, at least for me, it is easier to forget that, okay, I add something that is not Casimir and it breaks. So those two formulations are equivalent. I think this is more elegant. However, if you are going to apply it, this approach gives you more intuition how to do it. And in order to show the equivalence of those two approaches, it is enough to show that this composition is a Casimir. And indeed it is, because we take the composition of it, put it into Lie brackets. For A, take any smooth functions. Okay, by definition, it is a B vector derivative. We derive, we have a sum over the derivations. Okay, now we use bilinearity, and what we get is just the P vector of derivative of the Casimir with any smooth function. Okay, but this is a Poisson bracket of the Casimir and the smooth function. Okay, this is 0. Okay, so indeed the phi is also a Casimir, and actually you can just write H plus C and it will change nothing. However, in the example I will present, it is this notion with this is also you have bear in mind. It is worth bearing in mind. So, okay, what we now do is to compute the first variation on the full space. Okay, we compute it, and we evaluate it after we get computed on the equilibrium point and set it 0. And what we get is the equation system that determined our phi at equilibrium. Okay, so now we have a phi chosen so that the first variation vanishes. Now we compute the Hessian. Okay, so we compute, and now what we do is restrict this on the tangent space. So the equilibrium is formally stable if the second variation at this equilibrium is definite, positive, negative, when restricted to the tangent space on the symplectic leaf. And here is exactly where we are doing the quotient out. So instead of doing we take the quotient space manifold and we divide it by the group, we do this, just restricted to the tangent space of a symplectic leaf. And the symplectic leaf is just restricted by the Casimirs, as you can see. So now However, this approach fails in the infinite dimensional systems and nonlinear systems. So what we need is R-naught convexity, or other words, correctivity estimates. And this is basically saying, okay, if there exists constants greater than 0 on the neighborhood of the equilibrium, such that those two inequalities hold, then we can say, okay, if this first variation vanishes, second is strictly definite on this tangent space restriction, then this equilibrium is Lyapunov stable modulo of the symmetry group, and those with those constants. Okay, so now we apply it to the free rigid body. So consider a rigid body where the configuration space is a SO3 V group, and we reduce it to the using Lie Poisson reduction to the dual to the Lie algebra SO3. We consider P in the physical interpretation this angular momentum, and we also require this for the ease of calculation. Then the Hamiltonian is given in this form. In the E is inertia tensor, P is angular momentum. The Casimir is just the 1/2 of the P squared. And the relative equilibria are given of this form, where Ek is just a versor, because we consider 3 dimensions. Okay, so step 1. What we do, we construct the Casimir invariant function like this. We calculate the first variation, we evaluate at the equilibrium. The Casimir evaluates to this, where lambda is a constant. We now require that it vanishes, and what we yield, the condition for phi. Okay, first derivative of phi is given by this expression for every axis, and this guarantees that the PE, that is the equilibrium, is exact critical point of the augmented Hamiltonian on the dual to the SO3. Okay, now let's just assume for just ease of calculations that the equilibrium is a steady rotation along the principal axis, the third principal axis. So this is the equilibrium. And now we are calculating the second derivative. Okay, what we get is this matrix, and we need to determine the stability of it. Okay, but not so. First, we need to also evaluate it on the tangent space on the leaf. So, okay, when we do this, indeed, the second derivative vanishes, so we get rid of the third axis, and yes, so we restrict this to the tangent space, and this tangent space is defined in this. So what we get after the restriction is that the Hessian, what we need to tell about the definiteness is just to analyze this 2 by 2 diagonal matrix. Okay, indeed we do this. We need to determine whether this is greater than 0 or less than 0 for a different axis. And indeed, if we have this restriction and this is the equilibrium, then we have that major axis is positive definite and stable. Minor axis, the first one, is less than 0 negative. Definite, it is stable, and the intermediate are mixed, so it is indefinite. To tell whether it is indeed unstable or stable, we need further analysis, and because the energy method gives only this is only a sufficient condition. Okay, this is exactly why the second axis, the intermediate axis, is not stable. This is called Janinen-Binkoff effect, and you can do this by linearization and or using the recent discoveries by the Xiu, Shi, and Huang. They connected the instead of calculations, you can just study the topology of fibers of the Energy-Casimir mapping, and just do a stability proof by drawing. And this is another example of the Janin-Bikov effect. So yes, thank you for your attention. If you have any questions, feel free to ask them.
Okay, thank you, Daniel, for a nice talk indeed. Is there any question, remark? Well, as a stand, I have a question. If no one else wants, sure. Anyone?
Well, well, you did pretty well. Congratulations. Just a very minor comment of the different. You mentioned two equivalent definitions of Casimir. A third one would be that it's a function whose Hamiltonian vector field is identically zero.
So for
define the Casimir as like that the Poisson bracket vanishes, or that it's in that so a third equivalent definition would be that C is a function such that its associated Hamiltonian vector field is the zero section.
Yes, it would be other. I mean, it is indeed basically rewriting this in other words. But what this definition says, it also the consequences is that, for instance, in Dirac geometry, the Casimirs, when we consider Lie algebra with admissible functions, the Casimir functions are an ideal actually for it, and so on. And yes, thank you for this other definition. Indeed, it is also a very nice interpretation. Thank you.
Okay. Is there any other comment? Okay, I have one. Hey, okay, Arthur, go. Go away.
Okay.
Go on.
So to use this method, you need to have Casimirs. Is there any way of finding them?
No. I mean, you just have to guess. This is the biggest minus of it. I mean, yep. The only method I know about, and I don't think there's other method just by guessing.
I mean, there are methods using the Poisson vector. Okay, this is one thing. You could do it. You just have the Poisson vector, and you can get the kernel. Yeah, when you have the kernel of that, and you can determine. This is one of the methods. There are more methods based on Lie group actions, Lie algebras, and methods when the Poisson vector is related to some additional structure. So you can also look for Casimir. For example, if you have a Lie Poisson tensor, yeah. So what you can do is you have a Lie algebra, because indeed the Poisson bracket is just the realization of a Lie algebra. You didn't write it down, but when you push the Lie Poisson bracket, if you write in the coordinates, okay, is a Poisson bracket whose coordinates and a third time base of coordinates are determined by means of the structured constant of the Lie algebra. So in that case, the Casimir related to the Lie algebra will give you the Casimirs of the Poisson bracket. This is another thing that it happens in many applications. You could have it. Well, as I say, I mean, physical motivated examples that I could give you. And there are other methods. Okay, it's not that there are not. In general, you have ideas that are not very useful, that they can work. And in particular examples, with additional structure, you have methods to obtain them. So I can tell you, and you can use them. It would be fine to find more examples. Is there any comment, remark?
I have one more question. Could you comment on this? Maybe I missed it. Could you
Sorry, I've lost you.
comment on this question? Sorry.
Can you repeat the question? I lost it. There was
you mentioned convexity condition. Could you comment on that in your example?
We don't need actually the convexity in our example because it's an autonomous system. And yep, yep. In our example, we don't really need it as it is autonomous system.
But it's a matter of autonomous system or finite dimensional system.
Okay, so in infinite dimensions, the things might break, as here there might be like some kind of infinity and like some kind of explosions, and there might be an infinite gradient or something. So instead of dealing with this somehow, we just ignore it by putting those restrictions. And also, I haven't studied. I don't know exactly the difference between non-autonomous and infinite dimensional. However, well, it is when we have infinite dimensional, we use it because it helps us to just ignore the weird things that happen in infinite dimensions. And in non-autonomous, I think it just this is not enough, as we already studied the first and the second variation, and this isn't enough. I don't know. I'm sorry if I didn't answer your question.
Thank you.
Okay, is there any other question? But I just have a small one, okay? Could you comment on the final paper you talk about the topological methods for the Casimir energy method? This one by this, I think, the Chinese authors at the very end. Do you know what they do?
The topological?
Yeah.
Sorry?
Yes.
Here. You mean this article? Okay, so what they are doing is studying the image of the Energy-Casimir mapping. So the Energy-Casimir mapping is just a function. Okay, this is a function that takes takes from R2 to R, and what it takes basically is just the Hamiltonian and Casimir, and they output something in R, as I remember. Okay. No. In different. It was the other way around. So we have R3. We take some point, and with the Energy-Casimir mapping just evaluates this on this tuple. And by studying the topology of the fibers of this mapping, the fibers are just the pre-image of this. So HC, right? So by studying the pre-image, we can determine the stability of a system just by looking where the equilibrium is. And for instance, in this example, what we did in Euler top, because this works very well in three-dimensional system, that's why I chose the Euler top. This the Energy-Casimir mapping would look like this. And indeed, when you draw this, you what you get is that this is the one stable equilibrium axis. Here we have the heteroclinic orbits that are it is indeed stable. However, there are not like exact equilibria. And here in the middle axis, what we get just by looking is the middle axis is unstable, as the definition of Lyapunov stability here in the beginning, it is indeed stable, as the neighborhood of this is an equilibrium, this is an equilibrium. So this is and when this is satisfies the Lyapunov stability. However, as we go on, we don't this stability definition doesn't work, as we are not close to the equilibria. So indeed here is the unstable axis, and instead of doing calculations, you just study this mapping, and yes.
Okay, thank you. Is there any other comment, remark? So thank you very much, Daniel, for a nice talk. Let's go for the following talk. But Xavi, please